Hello, everyone. It's a pleasure to be invited to the colloquium of our own faculty. And today's topic is a combination of many things. So I have had, just a disclaimer, I have had COVID last week, so I will try to be consistent, but be generous. Please ask me questions in the chat during the talk. If you would like to ask something out loud, it's better to do it at the end of the talk. I will try to answer all your questions. In the meantime, I will monitor the chat. This was, and this is, a joint work together with Leonard Guida, professor from Bern University of Applied Sciences in Switzerland. And let me say also a couple of words about the title of the talk. So the first term in here is power indices. This is from cooperative game theory or public choice theory as well. Mainly we'll talk about the so-called Shapley value, which is also a popular tool in interpretable machine learning for ranking attributes by their importance. And that is why here you can see the word attribution. Our machine learning technique, the main one, which we are going to consider, is the so-called JSM-method or JSM-hypotheses. It's just a rule-based technique for classification, and a very basic one, I would say, because it deals with attributes, which may be considered as Boolean variables at the low level. However, there are some generalizations to graphs, interval structures, and so on and so forth. And as a main language, algebraic language, we will use formal concepts or formal concept analysis and applied branch of lattice theory. So let's start. One of the main questions in machine learning is related to supervised learning, how to classify things and how to explain why this or that object belongs to a certain class. So here is a popular example from one of the workshops on explainable artificial intelligence. You can see two pictures and they are illustrating wolves and dogs. So the question is which one you would like to adopt, and we know that wolves are quite dangerous animals. It's risky to meet them at in wild nature, while dogs are servants or friends of humans. So we need to somehow extract useful features, and we need them as an explanation why your technique thinks, your machine learning technique thinks that the dog is on the picture or the wolf is on the picture. But we'll talk about more basic classifiers than those which deals with images today. So let's talk about interpretable concept-based classification. This is the first part of the talk. JSM hypotheses are named after the British philosopher John Stuart Mill, and this technique was developed here in Russia and in USSR by the group of Professor Victor Finn in terms of inductive and deductive logic. Later on, Sergei Kuznetsov, being the part of that group, formulated this technique in algebraic terms, which gave this method some computational speedups or improvements in terms of complexity and so on and so forth. There is also connection between famous hypotheses proposed by Mitchell and between version spaces proposed by Mitchell and hypothesis, JSM hypothesis. So I refer you to the paper by Gunter and Kuznetsov. By the way, Sergei Kuznetsov is a professor of our faculty. And one of the other important things which we would like to bring into JSM method is interpretability with power indices, the so-called power indices. So here you can see some of the sources like Strumbel and Kononenko, Molnar, his online book on interpretable machine learning is also very popular introductory material here. Landberg and his collaborators, those who use the so-called SHAP, they proposed SHAP, the tool which is also based on the implementation of Shapley values, approximate, but it's quite popular for explanation of tree-based models and also some neural network-based models. The main question here, what are the most important attributes for classification of a particular object? Sometimes in interpretable machine learning, this problem is called local interpretability. Let's continue with more precise definitions of JSM hypotheses. As I told, John Stuart Mill, British philosopher and I would say logician, proposed several schemes of inductive reasoning in 19th century. For example, one of his well-known variations of method is the so-called method of agreement. If two or more instances of the phenomenon under investigation have only one circumstance in common, it is the cause or effect of the given phenomenon. So you may notice this is the 19th century, but the thing which is formulated here is quite close to machine learning techniques that you are well familiar with, I believe, like nearest neighbors or even popular causal inference is quite close to that. However, the key moment here is that the cause or effect of the given phenomenon, they might be an how to say, indispensable, discernible. So whether this is a cause or effect is not clear from the context, but we might think that this is the target variable to learn. So the JSM method was formulated and proposed and formulated in the late 70s as an attempt to describe induction in purely deductive form. I would refer you to read the paper by Professor Victor Finn. However, in what follows, we will continue to describe it in a language which is closer not to logic, I believe, but to the data analysis, to data mining. In terms of formal concepts, what the formal concept is, it consists of two sets of entities. the extent, the set of objects, and the intent. The intent is formed by all the attributes that describe the concept. You might think about the concept of furniture, then all the common attributes like the material, wood, can be attributed to the objects of these concepts, and all types of furniture will be in the extent. In FCA, in formal concept analysis, this JSM method is known as a rule-based learning techniques in binary case from positive and negative examples. And concept intent is just the set of attributes that implies a certain class, one of the two, the positive or negative. The question which we are going to answer is even not how to generate all such rules. Let's assume that we know the techniques, the algorithm. The main question here is to answer, do all the attributes play the same role in the classification of a certain example, and how to rank them? Game theory offers several indices for such comparison. Let me name a few: Shapley value or Shapley-Shubik power index, the Bansev index. Sometimes it is mistaken with Penrose index. They are closely related. There are even more like Degen-Packel index, but let's concentrate on the two. Now let's dive in formal concept analysis. This is the discipline emerged in Germany, inspired by French mathematicians, starting from Évariste Galois and Barbeau and Manjardin. It works with binary relations known as contexts. So what the formal context is, you might think that this is the data table, the source of our data. This is a triple which consists of set of three key elements: the set of objects, from German Gegenstände, objects, the set of attributes, from German Merkmale, attributes, and a binary relation between them, which shows that a certain object G has a certain attribute M. If we consider two sets, A and B, we can define the so-called derivation or Galois operator, prime operator. There are two, but we'll use the same notation for both because we can differentiate them from the context, whether we apply them to objects or attributes. So let's consider the set of objects and apply this prime operator to them, A prime. It consists of all the attributes which belong to all the objects simultaneously. So each M you can find among the attributes of each object A. B prime means that for all attributes from B, we consider all attributes from B and take only those objects which have all those attributes in common. So G here in the B prime definition is just an object which has all the attributes from B. Maybe some others, but the most important that it has all the attributes from B. A concept is a pair with the first component A and the second component B, such that all the objects from A have all the attributes from B, and vice versa. All the attributes from B belongs to all the objects from A. We call B its intent and A its extent. This is the naming which comes from France as well, I believe, from Port Royal logic by Arnaud and Nicole. But anyway, we may always add the word formal just to delineate them from delineate algebra and philosophy. An implication of the form H implies attribute M holds if all objects having attributes in H also have the attribute M. Those are our classification rules. But there are some details which we need to refine quickly. Let's consider the formal context with the set of objects G and the set of attributes M and some target attribute W, which does not belong to the set of attributes. So it's somewhat a separate attribute. The target attribute. This target attribute gives us a partition of G as a set of objects into 3 subsets. Positive examples, those which has this W as a target attribute. Negative examples, those which are known not to have this attribute. And also the set of undetermined examples, G tau. We do not know whether they have this target attribute or not. The goal is to classify the objects in G tau with respect to this target attribute. So it's very familiar problem, isn't it? It's just binary classification problem. But to unify it into one context, we need to introduce some auxiliary notation. K epsilon is just one of the 3 contexts. The context of positive examples, the context of negative examples, or the context of undetermined examples. The learning context contains only those examples for which we know their target attribute, either as positive or negative. So we have just 2 sets of objects. Here we have the set of attributes plus the target attribute, and we have extended binary relation. So it contains not only object attribute pairs from positive and negative relations, but also the target attribute for all the positive objects included. So here there is a Cartesian product of G plus and this set containing only one target attribute. There is also a subcontext of undetermined examples. So the whole classification context includes it. And derivation operators in this context are denoted by this epsilon as a superscript if they apply to the corresponding sets of objects and attributes. Now it's time to define the so-called positive hypothesis. A positive hypothesis is an intent of some concept in the positive context that is not contained in the intent of a negative example. So you may think that it's just the set of attributes, with a certain property. If we apply our derivation operator twice, we'll obtain the same set of attributes. It means it is closed, it cannot be extended. You cannot add any new attribute to it. So it's already maximal. And H prime, this is some set of objects which contains only positive and undetermined examples, but not, and maybe undetermined examples, but not the negative ones. A negative hypothesis is defined similarly. This is the intent of a negative context that is not contained in the intent of a positive example. It means that H double minus is equal to H. So this set is again maximal with such a property that the corresponding set of objects does not belong to any excuse me, does not contain any positive objects. But what if this condition is violated? For example, an intent of some positive context is contained in the intent of a negative example. In this case, such hypothesis is called falsified generalization. Okay, so the positive hypothesis, a candidate to be a positive hypothesis, it's called falsified positive generalization. Now it's time for examples. You can see many valued classification context. So it's not a binary relation yet, but anyway, we can scale it and transform it into binary attributes. Transform the context into the context with only binary attributes. We can see the target attribute and examples from 9 till 12, they are undetermined. So let me say a couple of words about scaling. How can we transform them? For gender, we'll introduce just 2 new attributes. For male and female, 2 binary attributes. For age, we should introduce 3 new attributes, young, middle, and old. They are also binary. For education, we should introduce, we have 3 values, 3 Boolean, 3 such Boolean attributes, higher, special, and secondary. For salary, high, average, and low. And for target attribute, we'll introduce W and not W for positive and negative ones, but we might ignore at the moment the set of undetermined examples. What we do next is as follows. We generate the whole set of concepts and we try to understand which ones are good hypotheses, which ones are falsified. Luckily, there is an order on the set of formal concepts or on the set of hypotheses. This order can be interpreted as to be a more general concept, to be a more general hypothesis, where we can find the most general hypothesis. Closer to the top of such a partial order, actually it forms lattice If you are interested in algebra, it means that for this is complete lattice, that for any set of nodes, elements of this lattice, you will find their suprema and infima. But let's explore the lattice on the left, for example. We can see some nodes which are colored. For example, there are two red nodes. Some of them are in gray. Some of them are still blank or white. What does it mean? If we consider the bottom of this lattice, it should include all the attributes. This concept should include all the sorry. All the attributes, and if there are no objects that contains all the attributes, it has an empty extent. But if we go up, we'll see that some of the nodes are labeled by objects. That means that the corresponding concept contains exactly this object. So G3 is here, and it's also labeled by some attribute. This diagram is described with the so-called reduced labeling. It means that here in this node, to understand what are the attributes describing this concrete object or set of objects, I need to collect all of them in ascending paths to the top of the lattice. So to collect the attributes which describe this concept with the object in its extent G3, I need to go to the top of the lattice and collect all the attributes on the ascending paths. That is F, which, as far as I remember, means female, me, middle age, then HE, higher education, and so on and so forth. So, but this is also written here on the slide. So the hypothesis given by the red node labeled by A is actually A. What was A? Let me go back. It was A. Anyway, it's the salary average. After scaling, I named it as A. So average salary, middle age, female, higher education. So this is the lattice, I believe, positive context. Yes, it's the lattice positive context. And this is marked by red. And red here means the maximum such hypothesis, which cannot be dominated by any other. So, for example, this hypothesis, female and middle ages, is falsified generalization, because we can find such an example among such a combination of attributes among the negative examples. You can go and check it just here, for example, G6, middle ages, and female. There is one more node in red. This is also the maximal non-falsified, or the minimal if we consider the size of the hypothesis in terms of attributes. Hypothesis which we can use. As for the negative hypothesis, such minimal ones are marked by, I would say, green, but anyway, we have 3 of them. There are falsified generalizations, they are in blank. And less general hypotheses, which are represented by single objects, they are here in green. They are not that interesting to us, so we are going to consider only this set of 3 from the lattice of negative examples and this set of 2 from the lattice of positive examples. The scheme how to classify undetermined examples looks as follows. If the intent, that is attribute description of some undetermined example, contains a positive hypothesis but no negative hypothesis, then it is classified positively. If G tau tau, that is the intent of a concrete undetermined example, contains a negative but no positive hypothesis, then it is classified negatively. If such an object contains both negative and positive hypotheses, or does not contain any, then it is classified contradictory or remains undetermined, respectively. As I told, it's enough to have only minimal hypotheses with respect to their inclusion order. Let H calligraphic plus, respectively H calligraphic minus, be the set of positive, respectively negative hypotheses, and they are represented by the set of respective attributes. So they are just sets of attributes. And we can try to classify our undetermined examples. For example, G9, female, young, SP, special education, maybe high salary, contains the positive hypothesis, high salary, and no negative hypothesis. That's why it's classified positively. G10, female, as for O, old, higher education, average salary, does not contain either positive nor negative hypothesis. That is why it remains undetermined. J11 contains 2 negative hypotheses and no positive ones, secondary education and male salary low. Just in case, let me recall that we deal with credit scoring application. So negative means does not provide the person with credit. G12 contains the negative hypothesis, only secondary education, and positive hypothesis, high salary. That is why it remains undetermined. Now it's time to talk about interpretable machine learning, and let me share with you the example from Christoph Molnar book on interpretable machine learning. The basic problem is a regression problem here. If we are renting company, we can provide the client with some offers, and one of the offers does not include living with pets, with cats. The other one does include such an option, and we can see the difference. So we may try to speculate what is the average price on the market and what is the added value of each of the other attributes whenever it is included or excluded. This is a very simple idea to how to consider attributes as players in a game. Lloyd Shapley provided the later known Shapley index special value, how to define the value of each such player in such a cooperative game. When players form coalitions, what is the fair value of the player added to the coalition? So what we can see here is just the difference of some value function for a set S of players plus some other player or attribute in our case, minus the value for the coalition without such a player. Here we can see also the combinatorial coefficient. So it might be explained in two different ways, one with permutations and another one with just by taking coalitions from the set of all players without a given player M. We are going to define its contribution, its value. And this notion have some nice properties, and there are theorems showing that this is a fair payoff for such players. But how can we modify it for our binary classification problem with very basic Boolean attributes? It should be easy, but the crucial component here is the valuation function, or the game, how people from game theory domain call it. So we have the context with such positive and negative examples. Okay, we have our target attribute. We propose the following definition for the contribution of attribute M into the classification of object G. We consider all the subsets of attributes of G except M. This part remains the same, almost the same as Shapley defined it, except that we have this coalition, and as a whole set of attributes, we have only those attributes that are contained in G. And our valuation function takes three values. One, if our object is classified positively. So again, the definition is repeated here. There exists a positive hypothesis, and there are no negative objects. There are no negative hypotheses, sorry, classifying this object. -1 if we have negative hypothesis, and no positive hypothesis contained in the description of such an example, represented here. 0 otherwise. And we assume that Shapley value remains 0 for every attribute which does not belong to G prime, to the description of our object. Let's check and see what are the Shapley vectors, that is Shapley values for all the given attributes for a concrete object in our example. So, for example, for object G9, we have a Shapley value equals to 1 for attribute high salary. So there is only one attribute with non-zero value, and it is 1. Actually, there is a theorem which says that for positive classification, the sum of all the values is 1. In case of undetermined example, we can see that Shapley vector contains only zeros. Sometimes you can see that there are zeros, and there are zeros with decimal dots. It means that those with decimal dot, with decimal point, are computed by formula, and those without it, they are just 0 by the definition. For the negative, for the negatively classified object, we can see that the sum of those values is -1. For contradictory classified object, this is a case which is not, for example, presented in Schaap by Landberg. We can see that the sum of all the components is 0. So it means that our classifier cannot say whether it's positive or negative, but it may show us those attributes with their importance values with respective signs. So that's why it might be a convenient tool to figure it out why our classifier is stuck. As for properties, it might be a statement or theorem, if you like. We collected some simple properties here. For positive classification, the sum of all Shapley values is 1. For negative classification, it's -1, 0 for classified contradictory or undetermined, and it's always 0 for every object which does not belong to at least one positive or negative hypothesis contained in G prime. This 0 contribution is also known as a contribution of the dummy player, the player which does not contribute to the game by any influence. Okay, let's experiment with, I would say, real examples, because it is an example from UCI machine learning repository on the zoo dataset. It contains about 100 examples, animals, and 70 attributes, plus target attributes. Some of them are non-binary, like the number of legs, but they can be treated as categorical attributes and scaled nominally. So they are binary, essentially, after that procedure. And we consider only binary classification problem, where mammals is our positive class, while all the rest from the negative class. So we have 41 positive examples and 60 negative examples. So the negative examples contain birds, fishes, insects, some other types of animals, but this is close to the scheme one versus the rest, just in our example. The positive and negative hypotheses are as follows. The positive are milk, backbone, and breath, which is quite obvious for mammalians. But the set of negative hypotheses is much bigger. For example, there are hypotheses like venomous or eggs and domestic. So you can easily imagine what are the animals that correspond to them. let's consider the attribute description of duck as our object. Duck has feathers, eggs, airborne, aquatic, backbone, breaths, 2 legs, and tail attributes. And it contains 2 negative hypotheses and no positive ones, so it should be classified negatively. Now let's have a look at its vector of attributes. The minus sign is out of the brackets. Inside you can see all the non-zero and zero values. We can visualize them with lollipop diagram in Python, where I implemented all the techniques. It's freely available on GitHub. You can find the links at the end of the slides. So the most important attributes are eggs, breaths, and airborne, while aquatic is not important in terms of Shapley value. It's not that important. So this that kind of diagram can be useful interpretation of classification results for true positive and true negative cases. Imagine that you deal with some medical diagnosis, binary classification problem, and you have during the training some true positive and true negative cases, and you will see the attributions, that is the values of importance of attributes with respect to this incorrect positive or negative classification, and you may try to understand why your classifier did such a mistake. The second part of the talk is about the so-called stability indices of concepts. It's shorter. And here again, we can use Shapley values, even though this is not a supervised setting anymore, it's an unsupervised setting. These indices were introduced by Sergei Kuznetsov just to understand how stable the found concepts or hypotheses are with respect to their robustness under object deletion. There are two kinds of such indices: intentional and extensional. So our question here is not only our main question here is answer how much important a certain attribute with its contribution to the stability index. Let's have a look at the definition of extensional stability index of concept. We have a concept, the set of objects A and set of attributes B, being the extent and the intent of the concept respectively. What we can try to do, we can try to test all the subsets of attributes, whether their double prime operator is equal to the whole set. What does it mean? We test, by doing so, we test how stable this concrete concept under deletion of some attributes. This set of attribute subsets such that their double prime operator is equal to the intent of the concept is called generators. Generators are well known in data mining, in association rules mining, as minimal sets which generate the whole set of specific properties for some association rule. And this index is between 0 and 1. There are also the so-called level-wise stability indices when the subset of attributes has a fixed size k, but its double prime operator is equal to b, the intent of the concept. And we can check whether each of such sets of size k contribute enough to the corresponding intent b. Enough again means whether the maximal value is 1 or it's somewhat smaller. Now we can also define the indicator function or valuation function for such a problem and compute Shapley value of a concept. Everything seems to be the same, but we do not deal with objects. We deal with formal concepts, with the set of attributes. Here we can formulate not the theorem, but maybe some statement which may help us to compute those values efficiently using their lattice properties, and doing so, by doing so, we can see that there is no difference here on the right-hand side for the value of a set plus a given attribute m and minus the value of this set. So this might be somehow a computational improvement, but I decided to keep this expression not by this reason. The reason is that we can find somehow the way how to connect stability indices and this reformulation with the help of lattices. So one of the reformulations contains the term where level-wise stability indices are in the first sum, while the value of some set D is on the right-hand side, multiplied by the corresponding combinatorial coefficient. And if our set of minimal generators contains only one minimal generator, the last sum is equal to 0. And moreover, the first component is just 1 divided by the size of a minimal generator. So let's consider examples again. As an example, I would like to present an example from the paper by Sergei Kuznetsov on formal concept analysis for machine learning. Again, it's very basic. It's about a robot with a manipulator, and this robot is designed to discern between fruits and non-fruits. And we also have some undetermined examples like mango. There are 4 attributes: color, firm, smooth, and form, round and oval, maybe cubic. Anyway, again, we need to transform those attributes into binary, attributes. You may think that it's somewhat like one-hot encoding in machine learning jargon. Here you can see the concept lattice diagram and the corresponding scaled context. For each color, we have exactly one binary attribute: white, yellow, green, blue, firm, not firm, smooth, non-smooth, round, non-round. And we can find, again, minimal non-falsified hypotheses among our concept intents. We can also find their stability indices. We can see, for example, in this first table, the corresponding concepts. Example 4 and all its attributes. Example 3 and all its attributes. The stability index, quite big, 0.62 something. But there is one more concept with the highest stability index. It contains the whole set of objects, non-firm. This property belongs to all fruits. However, by the definition of Shapley vector that we provided, its value is 0. Why? Because all the objects contain these attributes. So by our definition, it does not give any value to such coalition. Okay, it's also interesting to see that the concept with an empty set of objects, which has the whole set of attributes, has rather high stability, and the components, that is, values of attributes, are non-zero. This is also an interesting result, and we may think, what does it mean for our data analysis purposes? But maybe let's have a look at the similar result for the zoo dataset that was presented previously. There are more than 300 concepts in total, and the top 3 most stable are C1, C2, C3. Just one with the whole set of objects and 0 attributes, which is not really interesting to us. The one with the empty set of objects, but with the whole set of attributes. And its diagram, the lollipop diagram of Shapley vector, is here. And if we try to recall for what purpose Shapley vectors have been used in interpretable machine learning, local interpretability pops up, right? But here we have something like global importance, which gives us global ranking on the whole set of attributes. Okay, the third concept has some set of objects. They are listed, not the names of animals, sorry, but only indices. But what we can read from the attributes: feathers, eggs, backbone, breaths, 2 legs, tail. It seems that this is a concept describing birds. So only birds are represented here, and 3 is the most important attributes are shown here: feathers, eggs, and 2 legs. Okay, some concluding remarks. So Shapley values provide a tool for assessing attribute importance for objects classified by JSM method, and also for attribute importance for concept stability. There are some algorithmic issues, including approximate computations and scalability, So we cannot work with hundreds of attributes in a reasonable time, I believe, but with a couple of dozens it's still possible. So we may consider some approximate computation techniques like Landberg already did. The key difference, I believe, that we use different evaluation functions. We can also attribute such cases when our classifiers refuse to classify objects and see the reasons in terms of attributes importance. Some demos with Python code and IPython notebooks can be found at the GitHub project pages. There is also a demo recorded by some conferences on YouTube. So the last point is just an artifact because I shortened the presentation, but we can try to find something like well correlated or similar attributes and exclude them from our consideration. There are special techniques for this purpose. You can find their description in our joint paper written together with Leonard. Some citations from related papers are here. So we showed maybe a very basic scenario how to deal with rule-based techniques and Boolean attributes, but you can read Cynthia Rudin papers. She received a big prize for her contribution in interpretable machine learning, and she calls to stop explaining black box techniques and start use interpretable models instead. So our rule-based techniques, they were interpretable, but we added even one more layer of interpretability here by using the so-called power indices from cooperative game theory. I didn't show Banzhaf and Penrose indices, but you can find the results in our papers as well. Thank you.
Yes, thank you very much, Dmitry. Now we have some time for questions. Please feel free to unmute yourself and ask a question. If you have any.
Yeah, good evening.
Okay,
Good evening.
Yeah, hi, Dmitry. This is Anand.
Not nice to hear you.
yeah, fine. So I have one question. So did you work on any error handling function while classifying the data?
You mean what are the error functions that we use?
Yeah.
Maybe like through positive rate or quality indices like area under curve, right?
Okay.
Yes, we used them, but why we are not reporting them here? Because our main focus is interpretability. Yes, in a serious research paper before diving into interpretability issues, you need to provide that your model is at least good enough for a certain problem. So if it is credit scoring, maybe we would like to have something like 90% of accuracy, or maybe we even would like to have fair values for buff classes in terms of precision recall or some other measures. Yes, we measured them, but we do not report them here because we rather show how to attribute the contributions of separate features in our rule-based techniques. But I have to say that GSM technique is rather cautious. So in case when you cannot say whether this mushroom is poisoned or not, or whether the patient is ill or not, it refuses to classify. The example remains undetermined. It means that it's better to involve a human, and that's why we have introduced this technique, just to understand which features are the most important, and maybe human as an expert can do something with that.
Yeah. Thanks, Dmitry. Thank you. Yeah.
Thank you.
Thank you. There is one more question by Sergey Legovich. Yes. Can you?
Hello. Thank you, Dmitry. Yeah. The question, I understand the issues with complexity, so the scaling up. But I would ask these questions rather to the idea of the approach. This Shapley approach was designed originally for explaining black boxes, but JSM hypotheses and implications are not black boxes. Yeah. The only problems with them when the premises get too large. So basically, we are quite in explainable situation when the premises are constrained from above. Why not just going from this side? That would look much simpler, checking for, say, premises of size 3, 4, or other magical numbers the psychologists propose to us.
Yes,
What do you think?
This might be a fruitful idea. I agree. Sometimes we have only one hypothesis, and in this terms, as far as I remember, the ranking is flat. But if we have more than one and of different sizes, then we have something like this. When our lollipops are of different heights, right? So here it may have sense. But what you proposed, I believe, from computational point of view, is an attractive way to continue the work. Yeah.
And another question, I didn't realize, it would be nice to take the short dependencies, but sort of covering existing examples. What about covering? Does it somehow, is it somehow involved in the mode, in the mechanism, or you have to take care by other means about covering?
I think that we need to include it by some other means. We did not take it into account yet. No. Actually, we did 2 contributions. So we proposed 2 different evaluation functions, which seems to be reasonable. One for JSM hypothesis supervised case, and one for unsupervised case. Pretending that we can explain the contribution of each attribute into stability, but we did not take into account the coverage explicitly. Yeah.
Okay. Thank you.
It's okay. I also have a question. I'm sure it's a naive question, maybe not correct, but still. So you mentioned that it's rather computationally challenging to compute probably Shapley values or something else. And there are some approximate algorithms how one can approximate the solutions. And then the question is, can you still, so when you obtain a solution, can you somehow check it for like some interpretability, how good it is, how interpretable it is, something like this? I'm not sure I'm asking this correctly, but this is the direction of my question.
Okay. Among those examples that we have checked, there were some artificial ones where we know the structure of the lattices. Those are known as nominal scales, counter-nominal scales, and what we expected to see somehow correlates with our understanding of the data. So we have seen some patterns which more or less correspond to such model cases. But I'm not sure that when we introduce some approximate schemes, this will be such an approximation will be a good and well interpretable tool if we just simply copy the mechanism by Landberg. What they do, they just generate Frankenstein monsters out of existing examples, so they glued together their parts and generate artificial examples, so to speak, and they find approximate values. I think that here we cannot do that directly, because we may ruin how to say the idea of JSM method. So we may think that our data are clean enough and real good enough to find the dependencies in them, but if we approximate it with such an approach like Landberg proposes, we will ruin the exact meaning of hypothesis that we generate. Yeah, and in some measures of interpretability that can help us to control whether we are on the right way, they are needed, but we do not have. No.
Mm-hmm.